This video covers the topic of dry friction. Friction is a force that opposes motion, and it always acts tangent to the surface where two bodies are in contact. And friction has a magnitude that is up to the product of the coefficient of friction, which is mu, and the normal force, N. So here we have a block in the figure. There's a block on a surface, and the block has weight, and we're pulling on the block. And there will be a normal force keeping the block from moving up and down, and then there will be a lateral friction force opposing the motion. And depending on the coefficient of friction between the block and the ground and the magnitude of the force P, the block may or may not move. So when the block is not moving, there's a coefficient of friction, the static coefficient of friction, mu s. And once the force P becomes greater than mu s times the normal force, then the block will start moving, and the friction force decreases at that point. And that's because when an object is moving, it has a lower coefficient of friction. That's called the kinetic coefficient of friction, or mu k. So it's harder to get something moving when you're dealing with friction than it is to keep it moving. When we're working with friction problems, there are three different types of problems that we can look at. The first type is where there is no impending motion. In this type of problem, the number of unknowns is equal to the number of equations of equilibrium. And this is a problem where perhaps we assume that the object is not moving, and we say we have a block or a crate resting on the ground and we're pulling on it. Then we can use the equations of equilibrium to determine the magnitude of the force or the tension that we're pulling with, and then we can, the friction force. So, and then we can check with our friction equation to make sure that that friction force is less than this maximum value, the mu times n. So that's the first type. So here are the free body diagrams for that example problem. And we have 6 unknown values, and with 2 rigid bodies, that means we have 6 equations. 2 times 3, 6 equations. So we can solve for all these unknown values using just the equations of equilibrium. And then we can go back and check to make sure that FA and FC are less than or equal to NA times mu A and NC times mu C. And so that's where there's no impending motion. We just want to find out what the friction forces are and what the normal forces are, and then go make sure, once we're done, that the friction forces are less than mu times n. The second type of problem, we have impending motion at all points of contact. So here's an example problem, and we might know the mass of the bar in the picture and the coefficients of friction where it contacts the surfaces. And we'd like to determine what's the smallest angle theta that the bar can be at before it starts slipping. And so that would be impending motion, because if theta changes, it gets a little bit smaller than the bar would slip. So that's the definition of impending motion. And it's at all points of contact because it would start slipping both at A and B simultaneously. And so in this case, the number of unknowns is equal to the number of equations of equilibrium plus the number of frictional equations. So here, the reason we have the frictional equations, by frictional equation I mean Fs is equal to mu s times n. And so this is the largest value that the frictional force can have, mu times n. And that's why motion is impending, because once it's required for that friction force to get just a little bit bigger than mu s times n, then the object starts to move. So we'll have unknowns, NA, FA, which is the friction force at A, and NB and FB. And so that's and theta is the other unknown. So that's 5 unknowns, and we have 5 equations, 3 from the equations of equilibrium and 2 from the frictional equations. FA is mu A times NA, and FB is mu B times NB. So using those 5 equations, we can solve for all the unknowns, and the one we want most is the unknown theta. So we can find the conditions at which the object has impending motion. And the third type of problem is where we have impending motion at one of several contact points. So in this case, in the figure, we have the same structure or mechanism as in the first example, but now we're pulling on member BC, and there are 2 things that could happen. The first thing is that the mechanism could start to slide at C, and A would remain stationary. Or the other thing is that C would remain stationary and A would start to slide. And so that's the third type of problem, where we don't know which case is going to happen. And so in this case, the number of unknowns is less than the number of equations of equilibrium plus the number of frictional equations. So that total number of equations is more than our number of unknowns. And so the way we find out what's going to happen is we go ahead and try both cases. So we assume that for this example, we would assume that the object would slip at C, and so it would be stationary at A. And so then we would find out what the value for P is needed to make that happen, and then we would assume the other case where it's stationary at C and slips at A, and we'd find the value of P required for that case. So here we have 7 unknowns, 1, 2, 3, 4, 5, 6, and then P is an unknown because we don't know how hard we have to pull it to make it start moving. And so if we have 6 equations of equilibrium, 3 for each of the 2 rigid bodies, and then 2 frictional equations, so that's more equations than we have unknowns. So only one of those frictional equations is going to be true, and then the other frictional equation wouldn't be accurate because the frictional force will be less than the maximum value for the other point. And one quick note about the frictional force itself. So when we deal with these objects, rigid body objects, not a particle, the normal force is really a distributed load. So you can see that here in this figure. This is what the normal force actually looks like. It's a distributed load. There's, force per area or force per length over the entire contact surface. And what we do is we treat this like an equivalent force at a single point, just like with this distributed loadings that we've done in the past. And so what that would mean is that here's the force P, and here's the weight, and we would treat the the normal force like this, single force acting at a given point. And the way we find out where it is, the magnitude is just given by the force balance in the y direction, and where it is we can find out by summing the moments about a point, or summing the moments about a point. And so now we'll look at an example. So this is example 1 in the text, and we'll just work through it real quick. So we have a crate with a mass of 20 kilograms, and we apply this force P to it, and we want to determine if it remains in equilibrium. So that is, does it remain motionless? So this is a case where we have no impending motion. This is what we consider a case 1. No impending motion. So we'll draw the free body diagram. And no impending motion means that we will solve for all of our forces with just the equations of equilibrium. Here's P, and here's our normal force, and here's the weight. And we don't know this distance here. Call it x. That's unknown. And then there's a friction force that's opposing the motion. So there are two ways in which this could possibly move. It could, if P is big enough, then if the horizontal component of P is big enough, then the box could slide. And so that would be the case where Fs would have to be, is not big enough to overcome the horizontal force of P. And the other case where it could move would be if the normal force, in order to have moment balance, if the normal force, because the magnitude of the normal force is given by these two vertical forces, and the location of the normal force is given by the moment balance equation. And so if this x would have to be so big that the normal force would have to be outside of the footprint of the crate, then that means the crate would tip over. And so that's the other scenario where we could have the box not be in equilibrium. So we'll go ahead and find the normal force by taking force balance in the y direction. So we have normal force minus, and the weight is 20 times 9.81. And then we have minus 80 times sine of 30. And that all equals 0. So that gives us that the normal force is 236.2 newtons. And remember, for this case where we have impending motion, we're just going to use the equations of equilibrium. And so the forces in the x, we have P times cosine of 30 minus Fs equals 0. So that gives us that the friction force is 69.3 newtons. And now the other unknown is this value x. So we'll take the sum of the moments, and we'll take the moments about this point right here, call it O. So the sum of the moments about point O. We have 0.2, or negative 0.2, or the x component of P is going to generate a negative moment about O. So that's P times cosine of 30. And then the moment arm is 0.2 meters. And then N will generate a positive moment, so we have N times X, and that's equal to 0. So we know P and we know N, so we find out that X is equal to negative 0.00908. So that means that X is really right over here. So the normal force really acts right over here, and it's a very small distance from O. So that means that the crate can stay, it won't rotate about 0.0, because this value is less than half the width of the crate. If it was, the crate's 0.8 meters wide, so if X was greater than 0.4, then that would mean the normal force would have to be out here in order to balance the moments, which is impossible. So that would mean that the crate would be rotating. But since we found X is less than this distance, then the crate won't rotate. And we also need to check that this force is acceptable. So Fs needs to be less than or equal to the coefficient of friction times the normal force, and that is 0.3 times 236.2, and that's 70.9. So since this is less than 70.9, the crate doesn't slide either. So with this force, 80 Newton force acting at 30 degrees, the crate remains in equilibrium. And remember, that was the first type of friction problem where we have no impending motion. So the number of unknowns we solve for with the equations of equilibrium. And the no impending motion, it's also a case where you're just saying, is it going to slide? So you ignore the frictional equations until the very end, once you've found out the friction force, the necessary friction force, and then you just go back and check to make sure that that necessary friction force is less than or equal to the maximum possible value, mu n. So here's another example. This is fundamental problem 4. And we want to find the maximum force P that can be applied without causing this spool to move. So like the example we looked at earlier where we had the rod leaning against the wall and we wanted to find the smallest angle theta, here we want to find the maximum force P, and they're both impending motion problems at all points of contact. So this is a case 2 problem. So here the number of unknowns is equal to the sum of the number of unknowns for the sum of the equations of equilibrium and the frictional equations. So we'll start with the free body diagram. Got P pulling up the weight, normal force at B, and be careful to draw the friction forces in the proper direction. So they're always going to oppose motion. NA and the force FA. So we've got FB, NB, FA, NA, P, and W, and that's all the forces acting on this. So here the number of unknowns is equal to the number of equations of equilibrium and number of frictional equations. So we'll go ahead and start out with the two simplest ones. FA is equal to mu A times NA. And we get from the problem statement that mu A and mu B are both 0.3. And FB is 0.3 times NB. So now we can go ahead and substitute and just use these equations, or use these values instead of FA and FB. So we'll take the moments about, we'll call this 0.0. The sum of the moments about 0.0 is 0.6 P minus 0.9 times 0.3 NA minus 0.9 times 0.3 NB. That all adds up to 0. And force balance in the x direction. So NA minus FB is equal to 0. So NA is equal to 0.3 NB. And forces in the y direction, we have NB, FA, P, and W acting down. Those add up to 0. I should have substituted for FA, so NB plus, and so FA is 0.3 times NA, but then NA is 0.3 times NB. So we have 0.09 NB. FA is 0.09 NB. Plus P minus W is equal to 0. So we've used all 5 of our equations now. 1, 2, 3, 4, 5. And so now we should be able to solve for P, which is what we wanted. Okay, so we'll go up to this equation and get NB in terms of P, and then we can come back here and solve for P. Or maybe it'd be easier to use this equation. So 1.09 NB is equal to W minus P. NB is W minus P over 1.09. And now we can come up here and solve for P. And NA is 0.3 NB, so anyway, so there's everything in terms of P. And so we find out that P is 343 newtons. Because we know the mass of the spool is 100 kilograms, so we know W. So that was the solution for a case 2 problem, where we had impending motion at all contact points. And in these problems, we just want to find the condition where the object is going to start sliding, and we know when it starts sliding, it's going to slide at all the contact points. We'll work a couple more examples. So this is a case 3 problem. Or I'll call it a type 3. So here our number of unknowns is less than the sum of the number of equations of equilibrium and the frictional equations. So what we do is we try the different scenarios and find the lowest force P. So again, this is fundamental problem number 7. So in this case we're given the weights of the 3 blocks and the coefficients of frictions between the 3 contact surfaces. So AB has a coefficient, BC has a coefficient, CD has a different coefficient. And we want to find P so that the largest force P, or rather the smallest force P that will cause horizontal motion. And so there are 2 cases that we could have. One case is where B and C stay stuck together and they both start moving. And the other case is where C remains stationary and B just slides out from in between A and C. So we'll work both of those. But first, in both those cases, block A is going to remain stationary. So here's a free body diagram of A. It weighs 50 newtons. It has this tension holding it to the wall. And the block B is going to be pulling on the block A with a frictional force, and then they'll have a normal force at A. And the point of this is to just find that normal force at A is 50 newtons. So here's scenario 1. This is where B and C are both moving. So here's the free body diagram of BC. We've got the normal force NA, and that's 50 newtons, and we've got the weight of BC, and that's 40 newtons, because B is 25 and C is 15. And then we've got NC, the normal force between C and the ground, P, FA, and FC. So those are the frictional forces between A and B and between C and D. And the force balance in the Y gives us that NC is 90 newtons. And in the X direction we have that P is equal to the sum of FA and FC. So now we'll use some frictional equations. For this problem we would have 3 frictional equations, one from here, one from here, and one from here. But we're assuming B and C are stuck together, so we're not going to use that frictional equation. We use this one and this one. So that's why for these type 3 problems you don't use all the frictional equations. You don't use all the equations that you possibly can. Just use some of them. So for scenario 1 we're going to use these two. So FA is the coefficient of friction times NA, and so that's 0.3 NA. And FC, it has a different coefficient of friction there. It's 0.35 times NC, and so that's 31.5 newtons. So we can substitute back into here, and we find out that P is 46.5 newtons. So that's scenario 1. If B and C stick together, then we've got to pull with 46.5 newtons to get them to start moving. Scenario 2. So in this case, B moves alone. So here's our free body diagram of B. And it has a weight of 25 newtons. And we have this normal force, call it NB. And the friction force, FB, P, and FA. And here's NA, which we found was 50 newtons. So we'll just do the same thing. We have force balance in the Y. Gives us that NB is 75. And forces in the X, we have P minus FA minus FB. And then we use our 2 frictional equations. So we already know that FA is 0.3 times 50. So FA is 15. And FB is 0.4, because that's a coefficient of friction between B and C, 0.4 times NB, which is 75. And so that is 30. So then going back up into this equation, we find that P is equal to 45 newtons. So for this scenario, whenever P is 45 newtons, then we get motion. So we know that this scenario will happen before this one, because once we start off with P is 0 and gradually increase it, and once it gets to 45, then this block B will start to move by itself, and C and A will remain stationary. So this is the smallest force that causes motion, and it's in the case where B remains stationary. So again, for these type 3 problems where you want to find where there are more than one, where there is more than one way that motion can occur, you just go ahead and work through like each scenario. You assume one scenario and use the equations for it, and then you find out what the condition is for motion. And then you assume the other scenario, work through those equations, and find out the conditions for that motion. And whichever condition, you know, is a smaller force, for example, then that's the solution for when you have impending motion. And then the last problem we'll look at is this one. This is number 34. And so we have a crate with a coefficient of friction between the ground and also a coefficient of friction between the man's shoes and the ground. And so we want to find out if the man can move the crate. So we're just assuming that he pulls as hard as he can, and we want to find out if that force is enough to get the crate going. And so whenever you're looking to see if motion is going to occur, then that's a type 1 problem. So you'd say, you call it they're titled no impending motion, but it's basically a case where you're not looking for the limiting values, like, you know, what's the smallest angle before it starts to slip, or what's the smallest force before it starts to slide. Those are the impending motion problems. This one is where we're just finding out if it's going to move or not. So this is case 1, where we're just going to use the equations of equilibrium, or type 1. So you just use the equations of equilibrium to find the unknowns, and then you go back and check. Check to make sure that your frictional force is less than, you know, the maximum value possible. So here's the free body diagram for the guy. There's my person. Normal force on the man. Friction force on the man. There's the tension in the rope, that's 30 degrees, and the weight of the man. And so what we'll do is we'll find out here the biggest value for the tension that the guy can apply, and then find out how much it would take to move the box. So forces in the y direction, we have the normal force for the man, and we have t sine of 30, which is 1/2 t, and we have the weight of the man, and that all adds up to 0. And we're going to go ahead and assume that, like I said, we want to find the biggest tension that he can have, so we'll assume that Fm is equal to 0.4 times the normal force of the man. So that's the biggest it can be, and we'll go ahead and assume that it's the biggest it can be. So that's 0.4 times, the weight of the man is 784 newtons. and then we can get tension. So we have Fm minus T cosine of 30, which is square root of 3 over 2. And Fm is this value. So all that adds up to 0. And that gives us that T is 471.33 newtons. So that's the biggest horizontal force that the man can apply, or the biggest tension that he can generate. So that was sort of a type 2 problem, because we're assuming we wanted to find the biggest force the man can pull before he slides. So that part was kind of type 2. And then on the crate, we'll look at it as a type 1 problem, where we know the force, we know the tension on the rope, and we want to see if that's going to make the crate slide or not. So here's the free body diagram for the crate. So we've got the weight, the normal force, the friction force, and then the tension in the rope. And so we'll find first the normal force. (471) times the sine of 30 is half of 471. And then negative WC, and that's all adds up to 0. So we get the normal force of the crate. The weight of the crate is 150 times 9.81. So the normal there's our normal force on the between the crate and the ground. And then now we just need to check and see what the friction force is. So some of the forces in the X, we have 471.33 times the cosine of 30, which is square root of 3 over 2. And then we have minus Fc opposing that motion, and that's equal to 0. So that gives us that Fc is equal to 408.2. And our friction force says that Fs is less than or equal to 0.3 is the coefficient of friction here. So 0.3 times NC is 1235.8. And that's equal to 370. So the biggest friction force we can have here is 370, but we found that if we apply 471 newtons to this rope and the box is in equilibrium, or if we apply 471 newtons to the rope, then it would take a friction force of 408 newtons to keep this box in equilibrium. But that's more than our coefficient of friction and our normal force can provide. So that means that the box moves. So again, we had this problem where we had the man generating a tension on the rope, and we want to see if the box slides. So we sort of looked at it as two problems. First of all, we found the maximum tension the man could generate by considering that an impending motion problem. So that was like a type 2 problem where we'd have impending motion here at the ground. So we used equations of equilibrium and the friction force. And then once we had that tension, we just looked at the crate as its own problem. So we have the tension in the rope, and we have a crate, and we want to know if that crate is going to move. So that was a case 1 problem where we just used the equations of equilibrium to find the required friction force, and then we looked at the frictional equation to see if that was possible. And since we found that the required friction force was greater than what could possibly be provided, we know that the crate is going to move. So for these problems, we just want to know that the friction force is bounded by the frictional equation. The force is less than or equal to mu times n. And then we want to know those 3 types of problems and what to do for each of them. So we've got the no impending motion, we've got impending motion at all points, and then we've got impending motion at one of several contact points, and what to do for each of those.